Okay, yeah, thanks, Mona, for the invitation and introduction. Yeah, so my name is Tony, and together with Niels, it'll be my pleasure to present eMoflon Neo, eNeo, a fault-tolerant consistency management tool. Yeah, the tool is based on Niels' PhD thesis, so we use for evaluating that. So he's the expert. That means for any detailed questions, Niels will jump in. He's licensed to do that. And also in the chat, feel free to ask any questions. I think the deal is now if it's a simple question, Niels will answer on the fly. But if it's important, then he'll interrupt me, and then we'll clarify that. So I only have one screen and won't be able to follow the chat. Questions, as usual, are golden. So if you have a question, feel free to interrupt me, and let's discuss that. I don't need to. So I have, I think, enough to fill the time, but we don't need to go through all my material. Okay. Yeah. So the MDE community has a lot of tools, right? So that's not our problem. Maybe having good tools is a problem, but we have a lot. So it's fair to ask, what is eNeo as a tool, and why do we have yet another tool, right? So eNeo is an open source consistency management tool. Yeah, you can access it online, free to use. As a formal foundation, it's based on triple graph grammars. So I'll give a high-level intuition for what that is later in the talk. It also mixes integer linear programming, so search optimization-based techniques, and combines that with graph pattern matching. Right. So that's the mixture that we have in this particular tool, which should be unique. I think the mixture is unique. Yeah, it covers quite a lot. So a lot of MDE tasks. So modeling, meta modeling, graph constraints, model transformation by a graph transformation, and bidirectional model transformation. So consistency management, for me that's a synonym. Via triple graph grammars, so a certain style of doing that. And it does all this with a uniform language we call EMSL, so the eMoflon specification language. And it's designed to feel the same for all these different tasks. Another thing which explains the name of the tool, and maybe also the icon. I think the icon is now obsolete. So Neo4j has a new icon, I think. But it uses a graph database, in this case, Neo4j as a model repository. So your data is stored there. As a graph pattern matcher, so as a search engine, and also as a model browser. So that's Neo4j has a nice desktop. So it's called Neo4j Desktop. It's a model browser, and I'll be using that as well. I think it's also quite nice. Okay, then the important question, so why yet another tool? We already have quite a few, and why did we decide to build another one? So I have two reasons. One reason is, at this time in my life, I was still in academia, and I was holding or planning to hold a lecture on introducing model-driven engineering at Paderborn University in Germany, right? So I was looking for a tool to teach MDE, and the situation was there are many tools, right? So that means I think the lecture, so there was a lecture I sort of inherited and completely changed, of course. But what was being held before used 5 or 6 different tools. So basically almost every lecture you would take a new tool. And one could also argue for that. I think that's also pretty cool. So you get a nice overview. But unfortunately, I think that students were completely overwhelmed, right? So, and you also paid a very high price for getting to know a new tool, typically a different formal foundation or different style, different syntax, different semantics, completely different world. And that was, I think, very, very overwhelming, I would say. So my plan was to take exactly one tool and also base it on a uniform formal foundation. So I didn't want to switch between different types of, let's say, formal frameworks. So I wanted to use a single one for everything. And okay, that was one important goal. The second goal was I was supervising Niels' PhD thesis, which was fault-tolerant consistency management in model-driven engineering. There's a link at the ending, so you can take a look at that if you're interested. And yeah, so Niels, I think the primary goal of Niels' thesis was to to tackle consistency management. And we needed a very scalable platform, right? So that means we need to build up a lot of auxiliary structures and delete them quickly and so on. And EMF is a very nice framework. I love EMF. I don't think we have anything terribly better. But especially for this task, it was very costly to do this kind of stuff. And so EMF is a bit restrictive and enforces you to stick to the constraints of the meta model you're using. And so for the stuff we want to do, we need to be very free in a phase where we're calculating everything, and then we get back to a meta model conform state. But in between, we need to be super flexible. And graph database is something that is, I would say, better suited. Okay, so in a few words, again, the main points, right? So concerning teaching, tools are important for MDE. So MDE with paper and pen is, I think, not really, doesn't really make sense for 2022, right? But tools can also be a distraction. Yeah? So if you have too many tools or they're too complex, then the students spend all the time trying to get into the tools, trying to wrap their heads around the tools, and you miss or you waste half of your time doing that. All right, so I wanted to fully integrate an MDE tool in the lecture, but only pay the overhead for using exactly one tool. And that was my goal with ENEO, at least in the lecture. Final point, so using EMF and EMF-based tools with students, I got a lot of feedback concerning how the students wanted to work in groups, and of course use Git and diff things and use their favorite editors and so on. And it was important for me also to show that MDE tooling can be attractive for software developers, and that's also one of the goals of ENEO, right? So let's see the characteristics that sort of are implied by this. So first of all, only one tool for quite a lot of things, right? So it's not ENEO is not only focused on let's say triple graph grammars or consistency management. Yes, it has this focus due to Neil's thesis, of course, but still it covers modeling and meta modeling and constraints and so on. We'll take a look at that. So quite a few tasks are covered in the same tool. The next point is formalism. So my favorite, let's say, formalism for MDE is algebraic graph transformation. So there are many different ways to do graph transformation or formalized graph transformation. One of them is the algebraic way. And that's, so if you don't know what that is, but you know what basic category theory is, then that's it. Apart from that, it's just one way of doing things. But what I love about it is it covers everything, right? So it covers models and their relationship to meta models, and it covers constraints and patterns and pattern matching and rules, applying rules. And so all that's covered in the same sort of, in the same style, formal style. And I think that's very nice. When teaching, it's fantastic because you spend a week talking about patterns and pattern matching, and then you move on to rules, and the students profit a lot from what they've done in the last few weeks. So that's really nice. Okay, next point. The concrete syntax is 100% textual. So we use XSEX to design it, to build the editors and the tooling. And it's also designed for developers, right? So there's a read-only visual concrete syntax, very important for me. So I can't work without the concrete syntax and without the visualization. But I've also accepted over the years, many students just close that window completely and only work textually. And surprisingly, some people prefer this really. And I think for editing, it's actually quite great what you get from XSEX, right? Final point, Neo4j is taken as a model repository, graph pattern matcher, and Neo4j desktop as a graph browser. And as I said, the decision was on the one hand, of course, for the research Niels and I were doing, but it's also made the tool and the lecture more attractive for students, right? So Neo4j, or in general graph databases or NoSQL approaches, is something you can write on your CV, right? So it's something that enough people know about and is relevant enough with machine learning and data science and so on. So it's also nice to say, well, from the lecture, you also use Neo4j and have some experience in using this graph database that is already of industrial relevance, right? And so you can contrast that with some kind of pattern matcher that we developed ourselves. We have enough of that. That's also great, and in some cases even perhaps more suitable than a graph database, but it's not something that a student can sort of take on directly and write in their CV. Okay, which is an important point for lectures, I would say. I wanted to make it attractive. Okay, final point. Yeah, and this is related to research now. So I mean, towards Neil's PhD thesis, but also sort of taking a completely different approach to other existing TEG tools, right? So there are many different TEG tools, some of them in the eMoflon tool suite. So eMoflon is a kind of, let's say, umbrella for different TEG approaches. And yeah, there are other tools I've worked on that Andy and Lars are still developing and so on. So there are a lot of, we've tried different things out, let's put it that way. And if I had to say in which way Eneo is different, then I would say you can imagine other TEG tools as a kind of sports car. In this case, I think it's a Porsche. And Eneo is a kind of, let's say Jeep, monster truck kind of thing. Okay, so that means let's take a look at the characteristics, right? So other TEG tools have always had the primary, or well, in some cases primary, often very important goal to be super efficient and scalable. However, the downside of this always, in contrast to the theory, which is actually very generic and rather complex technical assumptions, right? So that means to use the tool correctly and really be efficient and get it even to accept what you want to do, you need to you need to understand and also adhere to these rather technical, not so trivial assumptions concerning usage and valid input, right? Okay. Eneo is different, so it's not by far not as efficient or scalable as the other tools if you use them right, but it's very tolerant with respect to usage and input, right? So that means there are almost, Niels, you can correct me here, there are almost no assumptions concerning the TEG and the input, right? So you can enter in, completely inconsistent, broken input, and the tool will do something reasonable with it, right? Okay, so for me, this is something new, right? So combining, let's say, the more formal approaches with search-based approaches, which are somewhat inherently robust. And after some years in practice, I can say, or in industry, I can say, it's not a bad approach, it's not a bad idea, because the real world also tends to be rather bumpy, right? So that means all these beautiful assumptions to get your efficiency and scalability, you need the experts, which you probably won't have, and the data, your input data, will also probably not be as clean as you would like. Okay, so let's talk about the agenda, right? So I still have quite some time. The first thing is I'll introduce a simple example, right? So a simple but realistic example. There's a link at the bottom. So that's a paper at the recent workshop on bidirectional transformations. And we discussed a few projects that I had in the automotive domain, and that had something to do with consistency management, right? So I've taken one of the example from one of these papers, simplified it, of course, but so it's not it's a realistic example, I would say. So it's something I've seen quite a few times. Yeah, and using this example, I'll go through briefly modeling and meta modeling with Eneo. Then we'll switch back to the slides, and I'll introduce triple graph grammars very quickly. Then we'll switch back to the tooling, and then I'll go through the other points and concentrate more on consistency management. All right, so let's go to the running example. Yeah, the running example is a general, let's say, case of concurrent engineering. So that means you have different developers, different experts, different people working on different parts of a system, or different, we could say, views of the system. And Of course, this makes sense, right? So more people can work at the same time concurrently. But the price is, of course, you have to make sure things fit together. So they eventually have to come back, and the system itself has to be consistent and has to make sense. Okay. So in the schematic picture here, we have on the left requirement management, and on the right, sort of more architecture. So in this case, component-based, design of your system. And we imagine on the left, so I don't want to name any concrete tools, a lot of concrete tools, but let's say something like DOORS or Excel even, right? So you might be surprised, but or maybe not. But Excel, if you often find that in practice, right? Still being used to write down requirements and sort through requirements and so on. That might be the case, you have to deal with it, right? What I'll be showing in the demo is sort of, if you wish, a kind of bytecode. So that means no one would work like this in practice. You would build, of course, a layer over your concrete requirement management tool and your architectural management tool and your testing tool and so on. So you'd have a layer on top of that, extracting the models, and the stuff I'll be showing will be sort of in the background. And so you won't expect, I won't expect real developers to interact with the tool in the way I'll be showing it in the demo. Of course not. It has to be, I would say, domain specific. So what they're used to. Okay, so on the left we have requirements in a certain form. On the right, we have a certain architecture. So let's say some kind of logical architecture or something. In any case, using component diagrams in some way. And things need to be traced to each other, right? So that means in this case, we might be forced by standards or norms in the domain, right? So in the automotive domain, in the medical domain, I can certainly say, you're forced to do this, you have to do this, you have to show that you're doing this and show that it's consistent. And let's call these connections traceability links. Okay, so that means for requirements, I need to know where are the relevant architectural elements for the requirement on the left. And okay, for the second requirement, it's being traced to a port and the component, right? So that's what I'm talking about in the requirement. Now, in the projects I've been in till now, the attempt to sort of keep traceability management or traceability links externally in a third tool or in a different tool, I have never seen it working, right? So I've never really seen it working in practice. So that means traceability links, at least the traceability links I've seen, tend to be manually created artifacts. So that means experts sit down together and create such traceability links. And to do that, they of course want very good tooling, right? So they want very nice integration in the tool they're used to working, and they want reports of the traceability, checks on the traceability links, and so on and so forth. Right? And typically, the tools that provide this try to do everything, and so it's a bit of a problem right now. So you might find a tool that is primarily for requirements management, or a tool that's primarily for architectural management. But they'll probably both try to solve the traceability problem. So they won't say, no traceability, you need another tool. I doubt if that's a very successful strategy right now. So that means you will have a solution for traceability management, but it'll be integrated in one of the tools, and you'll have to decide. So in this case, the decision was made, let's maintain our traceability links in the requirements management tool. And to be able to do that, we need some kind of representation of what we're tracing to, right? So those are the white sort of file-like elements. And so they sort of represent the relevant parts of the architecture in the other tool. And now we can trace, we can make traces in the requirements management tool and check them and run have a visualization and tables and matrices and so on, okay? So in the middle, sort of connecting both tools, are things that I now call correspondence links. Okay, so in the demo, we'll see them as well. And for me, those are correspondence links, whereas the traceability links that are costly and you want to maintain and check and so on, and not lose, and they can't typically be made automatically. I call them traceability links, but they're in one of the tools, in one of the models. Okay, and the challenge is both teams are working concurrently, right? So on the architecture side, we've decided to delete one of the ports, right? Maybe it was a bad idea and we've removed the port. It was problematic. We decided not to have it anymore. And at the same time, in the requirements, we've added a new requirement. Okay, so that's on the left. And I don't know if that was too fast, but we've sort of, probably the requirement was created by reducing a former requirement, extracting some parts into another file or another element or something. And that's why we've also changed one of the traceability links. Right? So blue is sort of changed, green is newly created, and red is to be deleted. Yeah? So this is, let's say, a snapshot of what has happened. And what we want is a tool to take this as input and yeah, try to make everything consistent. Okay, so that means help us integrate these changes on both sides and come to a consistent state. So let's call it a triple, right? So we have a left source model, and well, source and target left and right. Okay, just bear with me. But we have models on the left and right. We have correspondence links in the middle, and we have a notion of consistency that I haven't touched on yet. Okay, so there's some rules, for example, coverage rules, or yeah, okay, we'll see them in a moment. And the tool should try to help us check those rules and also suggest solutions of how to make things consistent. Okay. So if there are any questions up till now, I guess this could be a point where we cover them. If there are none, then I'll switch to the tool itself. So let's close this. Okay, so Eneo is an Eclipse plugin, right? As I said, built with Xtext, integrated in Eclipse, uses PlantUML for the visualization, if you know what that is. And yeah, it's completely textual, right? So this is a Java project, so it should feel a bit like sort of like coding. So let's start, right? So we'll switch to the real example later, but I just want to show a bit of tooling here, right? Okay. So let's create a meta model for the requirements. Yeah. And okay, so I'm also free to create a meta model for the architecture side of things in the same file. As you can see to the right, the visualization is also yeah, flexible, right? So you can mix. So I can have in the same file models and meta models and constraints and so on, and that'll all be depicted in the visualization. Okay. All right. So for requirements meta model, we of course probably have an element requirement, right? And the main part will be a description, right? So textual description, what is the requirement? We're not formalizing that, so there's no, you can just, so that will be sort of an informal string, more or less. But we also have an attribute is final, right? So we want to mark a requirement as being reviewed, let's say with a certain number of people or stakeholders. And as from that point in time, maybe we demand, so we have higher demands concerning coverage, for example, right? So we say, if a requirement is final, then please, it should be traced to at least a component and a port, right? That might be a kind of rule. Right? So, and if it's not final, then okay, then you're free to have missing traceability links for the moment. But as soon as you mark it as final, then it's no longer consistent if those links are missing. Okay, then let's add another element. So that's this, let's say, proxy, which is a representation of an architectural element from the other side, right? Then we want a traceability link, right? So this is, let's call it relevant 4, right? And it's connecting the architectural element to the requirement. Okay, so that would be a super simple meta model, but in essence, what I showed in the slides. Okay, so we have a requirement with a description and a kind of mark to show that it's final or not. And then we have these proxies for the elements from the architecture. And here we don't care what it is exactly. So we don't say if it's a component or port or subcomponent or whatever. Those are details for the other side. But here we need something to trace to, and this is kind of the proxy or shadow element or whatever. Okay, then let me do this as well. So here we have a component, also with an ID. I'm not going to be so strict with the IDs, right? So it's just a way to simplify the rules required. I'm not going to ensure, for example, that the IDs are really unique, right? So we have to rely on whoever is giving the IDs, just to keep things simple. Okay, but here we have the notion of subcomponents, right? So you have a hierarchical structure, and I'll also add ports, right? So, and that's to a port. I haven't defined that yet. So a port also has an ID. And I can also connect ports, right? Okay, so, okay, all right. So that's a simple meta model for that. So I have components with subcomponents for hierarchical structure. And I have ports and I can connect ports. And that's a very primitive meta model, but for the demo, that's enough. Okay, and just a brief reflection. So even though I don't use this tool anymore every day, but I can still say, well, it's if you can program, then you can click this together pretty quickly, right? So I hope you had the feeling too. It's not perfect, right? So the tooling can also still be, so students built this and can be improved. Of course, it's not exactly extremely professional software engineering, but it shows that modeling doesn't have to be, dragging awkward diagrams around and clicking things together, right? That seems to be kind of a feeling many students have, and that's just not the case anymore. Okay, so this should be fairly, I hope, at least very fairly, what you would expect from a meta modeling tool. Something I've always missed is being able to model directly, right? So even with the standard EMF tooling, you have your meta models, but when it comes to your models, then things tend to look different. They're not graphical anymore, and you feel what's this? It's a different syntax. What's going on, right? So that's why this is a bit. In yours, there's a bit different. So you can choose model right away. And let's call it requirements coverage source. Okay. And that's model, right? So it also pops up in my overview. And what I can now do is I can, using fairly similar syntax, right? So it's designed to feel similar, but instead of choosing the stuff from the meta model, I can choose a type from one of the meta models here. So I can choose requirement. And if I go out, then you see the overview also tells me, yes, this seems to be typed with this meta model, right? And that's the meaning of the arrow there. Okay. All right. I also get a warning immediately. So let's take a look. And it's telling me, so this object you now have in your model. It has a property description, and you haven't assigned any value to it. So something is wrong. I can already check the meta model and see that something is wrong with it, right? So let's add that. So let's say it's final false. And let's add the description. All right, so I can say, okay, right. So that's just an informal text, and and now the check passes, right? So that's just some simple checking for models. Also not perfect, could be better, but in essence, it's showing you could do this right away. Right? That's actually quite nice. My experience from teaching is also, if students aren't used to class diagrams or meta models, then they typically do funny things. But when they're creating examples or creating models, they notice, oh, this won't work. the way I meta modeled it won't work, and then they go back to the meta model and fix it. So that's always a very nice learning experience on that side. Okay, so I have a cheat here somewhere, so I won't bore you with typing in the models. Let me just copy them here. No, that's a bit too much. Let's take the model first. Okay, so those are the two models I have. So, okay. Right, so we have two models. Let's take a look at the visualization here. That's a bit more helpful. At least for me, right? Not everybody's like that. And okay, so we have this is the source model, right? So we have a requirement, we have three architectural elements, so the proxies. And there's a traceability link here connecting the requirements to A1. And we have correspondence links connecting the two models, right? So the packages are used to represent models, and those are correspondence links telling you which architectural element is represented as a proxy in the source model. All right, let's take a look at the target model. Yeah, so that's, we have a component, two ports, they're connected, and yeah, they all have their IDs, and that's it. Okay, then I would say let's, yeah, before looking at constraints, let's take a look at the, let's switch to the database and see what we can do there. So I can export the source model. Let's give that a try. So here you can see, so this is the outline, and I can say export to Neo4j.
Tony, let's briefly stop here.
Okay.
So there's a question in the chat. I think it just makes sense to answer them at this point.
Okay.
So the question is, where did the correspondence link come from? So it's not in the meta model, that's correct. But we have outgoing edges now from the source nodes to the target nodes. Maybe you can elaborate on that, and then we look to the database.
Yeah. Okay, yeah, nicely spotted. So the correspondence links are things that we need, right? So that means that there are quite a few, let's say, properties and some structure that we need for the tooling and connecting models and so on. And that's not explicitly typed in the meta model, that's right. So that means we have some, so I'll show it better in the database. So we have some meta structure on top of it. So every object is also an E object, and or a neo object or whatever, and we introduce all this extra structure on that level. Okay, so that means their correspondence link. That also explains why they're not, the typing is a bit, yeah, what should I say, a bit weaker now. So it's just a type and a string, and that's it. So that's some kind of, let's say, auxiliary structure that is, yeah, that we add to every object. Okay, and it's a bit, so the correspondence links are a bit technical, right? So users typically won't create correspondence links. You could be creating your traceability links, and the correspondence links are the technical stuff that the tool uses to connect models if we have to. Okay, I hope that answered the question.
Thank you.
But especially to explain that, so for example, when working with students, yeah, so you do all this stuff and it seems quite, yeah, I mean, it is a bit abstract, right? So as I said, it feels like a bit like bytecode. And okay, and especially things like this, where's everything coming from, and is this really defined? I can just write anything I want and stuff like that, right? And I would say the analogy to reflection or introspection in programming languages is the this MDE structure that we have. So this model, meta model, meta model, and so on to to make sure everything is typed. So the typing is closed in that sense. Okay, so let's take a look. So I ran the export. This can be done programmatically, but for a demo, it's still nice to have a button and be able to push it, right? So that happened. You know, so yeah, that happened automatically. And now I'm in Neo4j. So if you've never seen this before, it's a graph database. There are quite a few. They're also quite similar, I would say. So we could swap Neo4j with ArangoDB or something else. That would work. But Neo4j is nicely documented. There are also nice sources explaining how to use it and install it and so on. So that's it's a nice choice, at least for students. All right, so what we can do here is we have a bunch of node labels. So I can click on models. So let me see what models I have. And yeah, we get this structure here, right? So this is these are the models in the database and how they're connected. Okay, so let's take a look. Yeah. And so as you can see, this is the source model. This is the target model. These are the meta models, right, for each language. And this is yeah, meta model. Okay, so it's inspired by eCore, or we call it NeoCore because it's a little bit different, right? So let me just give one example of what's different. So we make heavy use of attributed edges, right? So the edges can be, your edges can have attributes, and that's incredibly helpful when you're dealing with correspondence links and also doing a lot of marking and unmarking and so on, right? So we make a lot of use of that, and the graph database can do that. So edges are first-class objects; they have attributes as well, and we didn't want to sort of, yeah, what should I say? Not make use of that just to be perfectly EMF conform. And so on that aspect and a few others, we yeah, the meta model is not exactly equal. All right, but this structure is explicitly here, right? So those are my models. And I also have a cheat cipher here to show all the models in, for example, the source, to show all the elements in the source model. So let's do that. So all elements in the model, let's take a look. Just need to put this there. So Neo4j has its own little language called Cypher. And I think it feels even more like bytecode, right? So that's why we have a layer basically on top of that. Okay, but basically this is the source model, right? So I hope you can recognize it now. So these are the proxies we have from the architectural model, from the target model. And this is the one requirement we have. So we can take a look at the details, right? So this is the description, it's final, okay. All right. So I could do the same with the target model, but I can also click here and yeah, and sort of pull the elements into place. Right? Okay. Yeah. Okay, and as I said, this will not only be helpful as a browser, at least for small examples, but also in a lecture, I found it extremely helpful that the students can sort of click around and play and really, hold on to the objects and links and inspect the structure they have there. I mentioned something about meta structure. So the meta structure is also here, right? So for example, if you look at this and you take a look at its labels, and you see it's also a NeoCore E object. So you can click on that. And yeah, so let's take a look. And so quite a bunch of different objects there, right? So these are now all the objects. But let's take for example, yeah, classifiers or something. So you could grab something, whatever that is now. Yeah, I think that's yeah. Okay, so basically you can explore the meta structure. I don't want to do that right now, and see how things are connected. Okay, so that basically you have the meta model as a graph, and the meta model also as a graph, all in the database and all, let's say, meaningfully connected. Okay, especially for the lecture, I also had there's a kind of flag you can set to create explicit type links, right? So you could also use that nicely to navigate the entire type structure. No? Okay. It's switched off per default because it's terribly inefficient then, but yeah, for demos, if you're trying to teach something, it's sometimes helpful to have that instead of looking at the labels. Okay, then the next point I have, let me check the time. Oh. The next point I have is constraints. Let me do that quickly. So again, it's a syntax chosen to be fairly, let's say, consistent with everything else, right? So we have a syntax for patterns. Right? So this is now, it's not a model, it's a pattern, right? And then you can build constraints on top of the model, on top of patterns, right? So I have a patterns for a short circuit. So a short circuit means I have two ports of the same component that are connected. That's not always wrong, right? So that's not always a problem, but for this case, it's just something maybe I'm interested in, or I don't want to have for a particular set of models. And I can model it as a pattern, right? So the pattern, first of all, doesn't say if it's bad or good, but then I have a constraint, no short circuits, and then I can say forbid short circuit, right? Okay. So there's a very simple, so basically you have patterns, and then there's a very simple constraint language on top of that, so-called graph constraints. And yeah, then you have a simple language to yeah, what should I say, to quantify over patterns. Okay. It also works in the database. So for example, I can take the no short circuit constraint, I can copy the Cypher query, right? And I can go to Neo4j and paste it. And then you'll see, so this would be the Cypher equivalent. If you're a Cypher guru, you could do this by hand. I'm not, so I don't even try. In general, I would say it's yeah, it's a bit more low level than the yeah, I would say the MDE stuff. At least I'm used to, right? Okay. But I can run this. It's executable, and it tells me the constraint is not fulfilled, right? So that means, yeah, it is violated in this case, so it doesn't hold, and that's true. So if we remember the target model, let's take a look at the target model. Yeah, so the target model has exactly those two ports connected. So, okay, so I could delete the edge, not directly in the database, unfortunately. And then, for example, export again or use a rule or whatever to fix the constraint, and then it would stay true, right? Okay. But I think we can move on a bit. Okay, so that was kind of basic stuff. So modeling, meta modeling, patterns, constraints, yeah, sort of typing of models with meta models, and so on and so on, and formalizing everything with graphs, and yeah, and graph patterns, and for pattern matching morphisms and so on, right? So that's something, that's the first, let's say, basic part of the lecture I used to hold. Okay, so let's move on to triple graph grammar. So we're now going towards consistency management, right? And what I'd like to use for intuition is string grammars. And if you don't know what a string grammar is, then a regular expression. Okay, so I assume everybody knows what a regular expression is, and that's okay. So if you can think of that, that's fine. Right? So a string grammar is a bit more than that, but in essence, it's okay to think of to imagine our regular expression. Okay. From a regular expression, you can have tooling that can extract or derive automatically a host of different let's say programs. In essence, they're programs, right? So you can have a parser, right? So something that checks given text if it can be if it can be described using a sequence of rules from your string grammar, or if it matches your regular expression, right? So that would be a parser checking that. Something you could also have is a quick fix, right? So if you look at Xtext, for example, then you can generate an editor from the grammar. And if you press Control Space, then it tries to help you a bit. So it has the regular expression or the grammar in the background and can guess what could be a completion of what you're doing right now. Okay, so that would be for me kind of quick fix. There are also pretty printers, right? So that means, yeah, in this case, if you mix, so from your regular expression or your string grammar, depending on the variant or dialect you're using, right? So that like think of xtext again, if you know what that is. You might extract some kind of AST or higher level structure. And the point is, in the grammar, you also have the information required to print that out again as a sequence of characters. Okay, so that's something that a pretty printer could do as well. And then the last point, also very interesting, is test data generation. Right? So there's some frameworks out there. So I think Quick Check is one of them that you can feed with, some kind of grammar or also regular expressions or something. And what it does is it can use that to generate a lot of test data. So in essence, examples of snippets that would be matched or would be part of the language. And you could then feed this into, for example, the parser. If you write the parser, maybe you've optimized the parser by hand, then you could feed it with this test data and say this should be detected as matching and this should not match, that kind of thing. Okay, so I hope everyone could imagine that. And the next, on the next slide, what I want you to do is to generalize this. Okay, so remember this, we have regular expressions and a lot of things we can derive from it. And now we generalize to a consistency specification. Okay, so we put a black box around it and we don't say it's a grammar, it could be a constraint, it could be a program, it could be anything. But its job is to decide, to define consistency, right? So that means if you feed it with something, then it should say this is consistent or not, right? So that means your consistency specification is what you need there. And given this, you can derive, or the goal is to derive a bidirectional transformation. Okay, so that means at the bottom part of generalize from all those things we saw. And in essence, what they're doing is checking for consistency, or in a more general sense, restoring consistency. Okay, so they take input and in the best case, manipulate the input to make things consistent again with respect, of course, to the consistency specification. Okay, so this is, we've zoomed out, generalized everything, right? So this is sort of the view, people working on BX have. Not all of them, so there's not always an explicit consistency specification, but in the general case, or let's say in many cases, this would fit. And what I want you to do now is, again, go down a bit. So let's get a bit more specific, but go in a different direction. So we're not going to regular expressions and, in essence, strings. We're going to graphs, right? So triple graph grammars would be one way to specify consistency, right? So grammar-based way. In essence, quite similar to string grammars, right? Just for graphs. Okay, but it's one way to specify consistency, right? And we now see a lot of things at the bottom of the slide. So we have a generator, right? So you can take a TEG and generate a lot of test data, right? So we have that also for the regular expression. We have correspondence creation, so we can provide a source and a target model and ask the tool to generate correspondence links in a way that consistency is restored as much as possible. Then, of course, we can just take the source model, ask for the completion. So that would be a forward transformation. We can take the target model, ask for the completion. That would be a backward transformation. We can say, please don't change anything. Just check if things are consistent. So that would be the check only operation. And the final operation here, called here concurrent synchronization, would be the task that I showed in the slide. So that means I give the tool a triple with changes in the source and target models. And then I ask the tool, please restore consistency for me. Make the triple consistent, right? You can do anything you want. We'll talk about that in a moment, how to control that. But essentially, I say, please restore consistency, and you're free to change at either side, and so on and so forth. Okay. In the tooling, I might use the term model integration. So these two terms are kind of synonymous for us. So model integration or concurrent synchronization. But if you see MI or model integration in the tool, then I mean concurrent synchronization, essentially the same thing. Okay. There are no questions on that, then I let me move on. So ENEO has a special hybrid approach to BX, right? So it's TEG based, but there's also something new to the approach. And yeah, so that's a train of research that that we've been working on that we worked on for quite a few years. And the idea is making things more robust, more fault tolerant, right? So that's Neil's thesis at the bottom of the slide. And the goal here is, well, not only to simplify the actual implementation of the tooling and thereby increasing trust in whatever it's doing, but also just to be more flexible for some of the operations, right? So something like a correspondence check, which is what we started with, right? So so Erhan Leblebici, his PhD thesis was on that. So at least one of the focus, one focus there was on consistency checking. And yeah, so there we sort of played around with search-based techniques. So using in essence constraint solvers to view correspondence creation as an optimization problem. So that's the point. We start optimizing and instead of programming a concrete algorithmic solution, let's say. Okay, but this is still input-output. So the input is an inconsistent triple and a change. So let's call it a delta, right? So you want to change, there are changes on both sides. And the output should be a consistent triple, right? What we do as a first step is we use the graph pattern matcher, so in this case Neo4j, to determine a superset of all reasonable or even sometimes all candidates via graph pattern matching. Okay, and we also apply rules, maybe, not the exact rules of the TEG, so I'll come to that in a moment, but we apply derived rules to build up this search space of reasonable candidates. And this is a critical step. And termination in general can be a challenge. Okay, so for example, in ENEO, it might be that it doesn't terminate. So it makes sense. I'll show that it makes sense to limit this step. So you can set a boundary in many different ways. But you can say, please limit the scope either in terms of time, so spend only 2 minutes, or please only apply each rule at most 10 times or something. So you can have those kinds of bounds, right? Yeah. Building on top of that, so that's sort of like this search space in terms of rule applications or matches. So those are the candidates. And what we now do is we build on top of this and formulate an optimization problem based on that, right? In this case, it turns out that an ILP is powerful enough to do this. So we only need an ILP solver. And we take the superset of all candidates, all rule applications as variables for the optimization problem. And then we encode the TEG semantics as constraints, right? So that means the rules of the TEG can only be applied in a certain way, right? So you can't create a port if the component is not there, right? Typically, or you can't connect it to the component if the component is not there already. And those kinds of constraints are then encoded as constraints for the ILP. So that will yield a result, right? So that means we pick a consistent subset of candidates that are correct in the sense that you could use the TEG to build them up, right? So they're consistent with respect to the consistency specification, in this case, a TEG. However, one last thing I have to, okay, right, so I'll get to that in a moment. First of all, the point here is so I feel this is a nice approach because it combines solvers and uses the right solver for the right task, okay? So the graph pattern matcher is a solver as well, right? So it's doing graph pattern matching, that's also constraint solving, but it knows what a graph is and it knows what edges are, and and it tends to scale actually quite well, right? So you can have many candidates and millions of nodes and so on, and that's absolutely no problem, right? And on the other hand, when you've made these variables, so changes, let's say high-level changes of the triple graph, and you feed that into so you've put ILP constraints on top of that, then the ILP problem is actually not that complex anymore, right? So that means the ILP solver can work on this higher level and doesn't need to handle deleting or adding individual edges in the graph, or for example, maintaining, even keeping the graph as a graph, right? So the ILP solver doesn't do that anymore. And that's nice. So there's some approaches out there that translate everything into an ILP solver. That's possible, why not? But yeah, it's you've pulverized completely the graph structure, right? So that means the ILP solver has constraints ensuring that edges aren't flying around, but they're actually connected to nodes. And those constraints tend to pile up. And and we feel something is wrong with that approach, right? So this combines things, and that's why it's a hybrid approach in that sense. Okay, so let's talk briefly about guiding the optimization, right? So I said it's an optimization problem. There are many solutions. So what's the best solution? We have to guide the solver somehow when it's picking out candidates. And what we do is there's an objective function, and we either punish or reward certain things. Okay, so that's what I'm going to go through now. So let's take a look at the resulting triple, right? So this is the resulting triple. Don't be confused with the colors. I'll explain that in a moment. But this is the result, right? And in this case, we would go through, and the objective function would say, well, you've preserved an unchanged element. For that, you get 1 point. Okay, so everything that's black here or gray is a preserved unchanged element. It was there before and it's there after, and for that you get 1 point. The red element is a preserved deleted element. So that means actually we wanted to delete that element, but Eneo has decided to preserve it. So that means in the result, to keep things consistent, it rejected the deletion, right? So it's allowed to do that, but there's a factor alpha, usually negative, that is used then to punish this choice. Okay, so usually you lose points for doing this. The next point is an added created element. So it's an element that was created, and we added it to the final result. So that's good. Right? So that's rewarded with a factor beta, and that's typically positive. I don't need to write that. Okay, and it's So we've normalized it with the 1 point for preserving unchanged elements. So you have to see everything in relation to that. So how much better is that than preserving an unchanged element? And finally, so that's why I made it dashed. The tool might add new elements that were simply no one created them. The tool adds them, induces them, we say sometimes, to maintain, to restore consistency, okay? And this is typically punished with a factor gamma, right? So it's usually negative, like alpha. And this simply says, how bad is it to add additional structure to the triples, to the models, that no one actually created explicitly? The users didn't create this. This is new structure that we say has to be there. So a bit like quick fixin has to be there because you want things to be consistent, right? Okay, and typically also in many reviewers typically criticize the fact that this is very how can you control this with only three parameters in general? And my answer is, of course you can't, but for Eneo we use these 3 parameters just to also gain experience. I mean, this is a new kind of tooling, but it can actually be made very fine granular if you want to, right? So that means many ideas have been basing the objective function on types, maybe even certain elements, maybe patterns or whatever. So that's possible to encode, right? So we also had a project with a company where we focused on correspondence creation, and the correspondence model was an allocation. So it was an optimization problem for solving an allocation problem. And in that case, the triple graph grammar was more or less fixed. So that wasn't changed all the time. But what was changed all the time were exactly these weights. So there was a DSL layer on top of the optimization problem where experts could encode very fine granular weights. So they could say, how bad is it for Mr. So-and-so to be on holiday and still get assigned certain tests, knowing that he'll only be able to do it in March and not in February, and so on and so forth. Okay, so that's something that's possible and was quite interesting in this context. Okay, then, unless there are questions on that level, I'll switch again to the tool and yeah, demo that a bit.
So actually, there are a lot of questions, but I think they are specific enough to answer them after the talk. So I think you should be all able to understand the rest, even without answering the questions. But we will come back to this later, and give a head start in the chat.
Perfect. Yeah, we're also 90 minutes seems so much, but we're slowly running out of time. So I think we have half an hour. So let me do the demo, and then make sure we have time for questions. That's great if there are many questions. Okay, so let's go back here. So I can close my cheat and go to the actual project. So I won't be clicking anything together, but I've already prepared a project here. And okay, so we have the two meta models we had before, right? So in separate files, but that doesn't change anything. So what's new is okay. Let me show the models a little bit. Right, so we have on the one hand, yeah. So a source model, also we've seen this before. So it's a single requirement and some proxy elements. Then we have the target model showing this this component with two ports connected. Okay. What we have here are two rules. So I'll be using them to create the correspondence links. So that means as a let's say more flexible strategy, instead of encoding the horrible, ugly correspondence links, you can just create them as a rule. And so I have here graph transformation rule, matching architectural element component, same ID, and simply creating the correspondence example. Okay, so that's correspondence links. One for ports and one for components and one for ports. Okay, so we'll be using that in the background. I think that's enough to start. So first of all, let's take a look. At model generation. So generating a bunch of models. I don't want to spend too much time on that, but basically there's an API for starting a generator, right? So you say which rules, and then you start up, and then you run the generator. In this case, so model generation doesn't terminate. I hope that makes sense for you. In general, it doesn't terminate in general. And that's why we have a condition here to limit how long it runs, right? So there are many ways, there are many different conditions, termination conditions one can implement. You can also implement yours. In this case, I'm using time. So it should run at most for 2 minutes, but I think I have a better one for the demo here. So I won't wait here for 2 minutes. So in this case, I'm just saying you can only apply each rule 2 times, okay? So let me run that. So this is now using the API, right? So I'll just run that as an application. And while it's doing something, I'll take the chance to show a bit what the generator is working with, right? So that means for every operation that we have, we derive from the TEG rules, so from the triple graph grammar rules, graph transformation rules. Okay, so yeah, we'll take a look at the TEG rules, and then I'll show briefly what we derive in each case and what's happening on the other side. But let's take a look at the database first. All right, so let me see what I can reuse here. Yeah, that's nice. Let's take a look at the target model. Oh, I think I also have a cheat here for the triple. So all elements in a triple. Yeah, that's right. Let's take that. Okay. So let's take a look here. So this is random, random data, more or less, right? So it's, we know it's consistent, but yeah, this is what it generates. So the yellow things are components. Yeah, you see, so there's some components, there are also some subcomponents, right? A few ports and the connection to the other side. Right? So in this case, this is a requirement without any connection. That's perfectly okay. So according to our notion of consistency, which I'll show in a moment, that's perfectly okay. Something I'd like to highlight, so this is an interesting case. So as you can see, there's a double edge, right? So if you're used to EMF, you might have the expectation this is not possible. So with ENEO, this is possible. The graph database has no problem at all with that. Sometimes also helpful. So if you don't want this to happen, so two edges that are basically the same of the same type, then you need to explicitly forbid it, right, with a constraint. Okay, so let's go back. So that's data, right? So that's a generator. And I think it makes sense to take a look at the triple rule. So this is basically exactly what the generator is using, right? So it's applying more or less exactly these rules, okay? So a triple graph grammar is a collection of rules, right? So it's a grammar set of rules. You specify the source and target. That's just a label, right? So it doesn't really make a big difference, but you basically call one metamodel source and the other metamodel target. You could call it left and right. Then you define some correspondence links, right? So these are the technical links, right? So in this case, link to port, link to component. We want to be able to differentiate between these kinds of correspondence links. And then you have a bunch of rules. Okay, so these are the rules that we want to be part of our grammar. Okay, let's take a look at the rules. So this could be a rule, right? So green means I'm creating something. And if you apply this rule, it simply creates a requirement that is not final in the source model. Okay. So let's take a look at another rule. All right, so this rule, also operating only on the source model, would create a traceability link. Right, so this rule creates a traceability link. Okay. Then we have a rule to create a final requirement. That's a bit more interesting. So what this rule says is, if you want to create a final requirement, so a requirement that has been reviewed, then you can't just create it like that. That would be inconsistent. You need to make sure that it's connected to a port, so to a proxy that is actually a port, and to a proxy that is actually a component. Okay, so that means if you don't do this, then you have something that is not consistent because you wouldn't be able to create it with the generator with the TG. Okay, so I don't think we need to go through all the rules, but in general, this is what's happening. You're describing how one could, so change, or let's say generate, so not exactly change, to generate the connected models in a way that after every step, so after rule application of the TG, you are consistent. That's obviously not how you work, but this as a basis, this can be used as a definition to derive all the other stuff that we're interested in. So restoring consistency uses this as a basis, okay? So I think the only thing that's maybe interesting is you can transfer, so you can have also checks for attributes on each side. I think that's maybe to be expected, right? So here, what we're saying here is, hey, if you create a port in the architecture, you have to create a proxy on the other side. So there must be some kind of representation on the other side. And by the way, it should have the same ID. Okay. All right. So that's the TG we have as input, so the consistency specification. And we derive, operational rules. We call them operational rules. So that's normal graph transformation rules representing exactly that, right? So let's take a look at the gen rules, right? So these are graph transformation rules, not triple graph grammar rules anymore. But in this case, they essentially look very much the same. Okay, so as you can see, so this would be creating the requirement and setting, the name of the model and stuff. But essentially, this is exactly what the rule was doing. And that's true. So for the generator, it's almost exactly the same as a TG. So let's do something a bit more interesting. So so before I switch to model integration, let's do consistency creation. Okay. So what I'll do now is I have a breakpoint set. So let me run this in debug, right? So that means what's happening is I'm clearing the database, pushing in the source model and the target model, and they're not connected via correspondence links, right? So let me show that here. Yeah, now, so as you can see, the proxies, so the architectural elements are not connected to anything. I'm double clicking on them and they're not connected. And so the correspondence links are missing, right? And if I now take a step in the debugger, right, then the generator is called. So for us, it's always a generator. So it's always a generation process. Whatever the operation is, it's a generation process. Just that the rules it's using are different, and the ILP problem it's solving at the ending is also different, and so on and so forth. So everything is configured, but in essence, it's always a kind of generation loop. Okay. So here we have a kind of report telling you how long it took, where exactly the time went for it, right? So this is interesting. So it took 3 seconds. In this case, I guess falsified because I was debugging, okay. But what is always interesting is the ILP solving, comparing that to the pattern matching. So those are the two solvers we're using. And it's always interesting. So it's impossible. I think that's Neil's conclusion. It's impossible to say what scales better, what will be more costly. It depends on your TG, depends on your meta models, it depends on your constraints. And we've had all cases, right? So sometimes the ILP solver is burning, sometimes the graph pattern matcher is burning. Yeah, it depends on your problem, right? Okay, but if I make an update here, then you'll see it has connected things as expected, right? And yes, the connection is simple, but it's not completely trivial. Okay, so we saw that if you have, for example, a final requirement, then it won't allow any kind of mapping. So it'll demand a certain number. Okay, so that was correspondence creation, and now let's get to the to what Neil's focused on his thesis, and that is the concurrent synchronization. Okay, so let's take a look at this triple. And bear with me, it's a bit, as I said, feels a bit like bytecode, so I have to explain a bit. So in essence, we have the triple I showed on the slides, but with a kind of markup. Okay, so there's some special attributes used here to mark changes. Okay, so so for example, this means that this element was created, right? So the architectural element was created. The traceability link, so the link was also created. So as I said, links can have properties, right? So the link there is also created, set to true in that case. And in the target model, one of the ports is deleted, right? So P1 is deleted, right? And yeah, and P2 is created, okay? And so I'll explain that in the database. Okay. But basically this is the input, so it's a triple, but it's also annotated with markings, encoding the changes, right? So the changes that the people made and what should be made consistent, all right? Okay. So what I'm going to do here is I'm going to also run this in debug, right? So that's that. So in this case, I'm pushing the entire triple, right? So this is the view before restoring consistency. Let's take a look. Okay, yep, okay. So I can also take a look at the the markings, right? So let's take a look at that. So this is P2 is new. So P2 was newly created, and that should be handled. The problem with P2 is it doesn't have a correspondence on the source model. So that's actually not consistent. So that has to be made consistent somehow. Either removed, so that could be possible, it just kicks it away. Or it could be, yeah, let's say translated to the source side, meaning it gets a representation there with the same ID and connected to the correspondence link. Okay, so that's a decision to be made there. This was there, should be preserved if possible. This should be deleted, right? So the underscore D underscore means this should be deleted. And that's also the question, right? So do we delete it and propagate the deletion and remove this? Or do we keep it? Now, it depends on the weightings we have for the objective, the weights we have for the objective function. Okay? But interestingly, this should be created as well. And as you can see, it has been chosen such that the IDs match up, right? So that means if you set the weights right, and we have, then the tool says, oh, this was created and this was created, and they chose the same, whoever did this chose the same ID. So probably you want to link that up, right? And let's see if that'll happen, right? Okay, so I can run. And okay, yeah, so that's, yeah, so you also get a report, right? So it tells you your triple is consistent. That should always be the case for concurrent synchronization, right? If not, something is wrong. And it tells you which rules were applied and in general, how good the solution was. So this is a kind of indication of the final points it was able to get, which should be optimal, right? And also a bit of showing you what time did it spend doing what. Okay, then let's take a look. Okay, and in this case, yeah, so it brutally simplified the model, right? So it rejected the creation, cleared out the deletion as well, right? And left us with this bare triple, which is consistent. Yeah? So it's not a bad result, but it's perhaps something we weren't really expecting, right? So let me, as a final step, then we're done. Let me show that there are parameters here, right? So yeah, so this is, so right now I have -1, -1, -100, right? And what I'm saying is, please never ever induce structure that no one created, right? Or that wasn't there before. That's why the tool is a bit inflexible on that side. So let's do this. So apply. And I believe we build afresh. Okay, and I think I can just run that directly. So if everything worked correctly, then we should also see that the solution is in general, I think, a bit better. Yeah, no, so we had a solution value of 5, now we have 24. That means the tool is just a bit allowed to do a bit more and restore consistency a bit more in a flexible way. So let's take a look. Let's take a look at what it did now. And yeah, okay. So in this case, it's allowed to induce a correspondence link, right? So this was added, the IDs match up. That's beautiful. Those are candidates for a correspondence link. Why not? So that's a suggestion. It's suggesting, hey, you created this and you created that. Maybe that's what you meant, right? So I'm now suggesting this correspondence link, right? Okay, that's it for the demo. And yeah, let me already say thanks for listening, and let's switch to questions. Can't wait for that.